Now that we've learned the equations that we can use to calculate different amounts of energy, we can use our energy conservation diagrams to solve some interesting problems and calculate specific amounts of velocities and heights and things like that. So let's look at example number 8 in Worksheet 6F as the first example of that. So here it's talking about a cart that moves, and I'm seeing it go to the right, and as it moves to the right, it runs into a spring, and then it's going to compress that spring. So at position A here, the cart has a velocity of 5 meters per second, and at position B, it says that the cart is motionless, so the cart is not moving. At position A, let's see, the spring hasn't been touched yet, so the spring is relaxed. In position B, the spring is compressed. And they're telling me to assume no friction. And I guess that's really all that I need here. So they don't tell me what to put in the system. And so I'm just going to put everything that I see here in the system. I see a cart that's on maybe some table. I see the spring. And of course we always put the earth. Okay, so this system, the cart with the spring on the table, how is the energy stored at position A? You know, I don't see any EG because I don't see the height of anything changing. I'm going to consider kinetic energy. Well, I do see the cart moving in A, even though there's no movement in B. Is there any elastic potential energy? Well, not at position A because there the spring is relaxed. Okay, so I think that at the beginning, all of the energy is stored as kinetic energy because the cart is moving. And at the end, all of the energy is stored as elastic potential energy. The cart is no longer moving, but now the spring is compressed. And so I'm going to write the conservation equation. The change in the kinetic energy of the cart equals the change in the elastic potential energy. Okay, so now I have a description of what's happening, and I've got an energy conservation equation. Can I use it to determine the maximum compression of the spring? So the first step is I take this equation and I'm going to replace the types of energy with the way to calculate that energy. So the kinetic energy I would calculate as 1/2 of the mass times the velocity squared. Elastic potential energy is 1/2 of the spring constant K times the displacement squared. And look, what it's asking me to find is the compression of the spring. I'm going to be solving for that delta X. It's a good idea to circle what you're going to solve for, right? I should have enough information to plug in the mass and the velocity and the K. And as I plug in, I'm going to make sure that everything is in standard units. So they gave me the mass of the cart. It's 8 kilograms, okay? Kilograms is a standard unit. The velocity is 5 meters per second. Again, I don't have to convert it. Meters per second is a standard unit. Remember to square the velocity. Let's see, did they give me a K? They sure did. 50 newtons per meter. Again, standard unit, so I don't have to do anything. And then delta X squared. That's what I'm going to solve for. So I have that delta X, you know, when I solve this, remember to take the square root, is going to be 2 meters. Okay, let's do another one. So here in number 9, we've got a rock. It's being shot with a slingshot vertically straight up into the air. And so at position A, the slingshot is stretched. It's pulled back. And the rock is at rest, and it's on the ground. I know it might not be quite on the ground, but look right here. They're telling us it's at a height of 0, okay? So we're not going to put any EG in it at the beginning. But at the end, the slingshot is relaxed, right? It's just a rubber band. It goes back very quickly to its original shape. Oh, the velocity of 0. We must be at a peak height, right? So it has gotten much higher, and we're looking at it at the point where just for an instant the velocity is 0. Okay. The problem doesn't give me a definition of the system, so I'm going to put everything that I see here in the system. I see a rock. I see the slingshot. And I see the Earth. Okay. At the beginning, the slingshot is stretched. And there's no EK because it's not moving. The rock's not moving. There's no EG because it's at a height of 0. So all of the energy is originally stored as elastic potential energy. At position B, there's no more EEL. The slingshot is now relaxed, so that is not there anymore. But the rock is very high, so there's gravitational potential energy. Okay, so all of the elastic potential energy, which we saw at the beginning, is now redistributed, and it has been stored as gravitational potential energy. And the question is, what is the peak height of the rock? Okay, so I'm going to calculate each of these things. So let me write the formula for each one. To calculate the elastic potential energy, that's half of the spring constant times the displacement squared. The gravitational potential energy is the mass times g times its height. What I'm solving for is the peak height, so I'm going to solve for this h. Okay, as I plug in, I'm going to be really careful to make sure that each thing is already in standard units. They gave me a K as 100 newtons per meter. They gave me the displacement of the slingshot as 0.3 meters. Okay. Here's one I have to convert. They gave me the mass as 500 grams, and I need it to be kilograms. So I know that 1 kilogram is 10 to the 3rd grams, and so that's going to be 0.5 kilograms. G is 9.8, and I'm solving for H. And so I get 0.918 meters. Okay, let's do another one. Here we have a roller coaster, and it wants us to find the final velocity of the roller coaster. Okay, so let's see here. At position A, it is not moving. It's very high. At position B, it's fast. It's moving very quickly, and it's on the ground. It's gone down to a height of 0. Okay, I'm going to put the cart, the track, and the earth. Basically everything that I see, I'm putting in the system. And so initially, this system, all of its energy is stored as gravitational potential energy, right? Because the cart is very high. Okay. So this is interesting. Let's talk about how to handle it. It says 10% of its energy is dissipated due to friction. Okay, so E-dis, the amount of dissipated energy, is going to be 10% or 0.1 of the gravitational potential energy at position A. Okay, because it's saying 10% of that original energy, which was all stored as gravitational potential energy, gets dissipated. Okay, so I'm going to have some dissipated energy here at position B because of friction, but mostly we're going to have kinetic energy because it's going very fast as it gets to the bottom of the hill. Okay, so the change in the gravitational potential energy is the change in the kinetic energy plus the change in the dissipated energy. Okay, so it's asking me to find the final velocity. So let me see how I'm going to calculate each amount of energy, and then I'll circle the velocity that I'm going to solve for. So the gravitational potential energy I find as mgh. Kinetic energy is 1/2 of the mass times the velocity squared, and E-dis I'm going to just calculate as 0.1 of that original gravitational potential energy, which is mgh, right? So the thing I'm going to solve for is this velocity. That's what it wants me to find. So I'm going to take all of the mgh's and move them to the left-hand side. So I've got 1 mgh minus 0.1 mgh. That leaves me with 0.9 mgh on the left, and that equals 1/2 times the mass times the velocity squared. So now I'm going to start plugging in. Let's see, the mass is 40 kilograms, g is 9.8, the original height is 5 meters. Here is the mass again, and v squared. So I just need to solve for the v. Remember to take the square root as you solve for it. So 0.9 times 40 times 9.8 times 5, and then I'm dividing by 1/2, I'm dividing by 40, and then I'm going to take the square root. So the velocity is 9.391 meters per second. For the sake of time, I'm going to skip 11, but I want to do number 12, and then that'll be finished. This is an interesting problem. So you're driving your car, and someone else cuts in front of you, so you have to throw on the brakes to stop. And when you do that, your car leaves a 26-meter-long skid marks on the road as it stops. And then a police officer comes along and gives you a speeding ticket. Claims that you were exceeding the 15 meter per second speed limit. And so we're trying to see, is that true or is that not? So let's think about this. At position A, you are moving. We don't know the speed yet. We might need to find that. At position B, you have stopped. Let's see. It doesn't talk about any change in height. There definitely is friction, right? Otherwise you couldn't have left those skid marks. Okay, and also they gave us a coefficient. Kinetic coefficient of friction is 0.7. Okay, so let's look here. Let's just put everything in the system, the car, and the road, and the earth. And at the beginning, the car is moving. Maybe too fast, but it's got a lot of kinetic energy. At the end, it's stopped. There's no more kinetic. We left long skid marks, so there was a lot of dissipation from overcoming friction to stop. And so basically, the change in the kinetic energy equals the change that we see in the dissipated energy. At this point, it would probably be good to go back to the slides, and let's just see that there is an equation for calculating the dissipated energy. The dissipated energy is the friction force multiplied by the path length. Okay, and so we may need to use that in this problem. Okay, so I'm going to calculate the kinetic energy as half of the mass multiplied by the velocity squared. The dissipated energy will be the friction force multiplied by the path length. If we just think about this car, I mean, I'm not really doing a nice force diagram, but the weight of this car is its mass, 1390 times 9.8, which is 13,622 newtons. And in this case, that weight is being balanced by the normal force of the road supporting the car, which is also 13,622. The friction force would be the kinetic coefficient multiplied by that normal force. So it would be 0.7 times that 13,622. So the friction force is 9,535.4 newtons. Okay, I just needed to do that because I see I'm going to have to put the friction force in as I'm solving over here. The thing that I'm looking for, because I want to be able to tell that policeman I was not speeding, I'm going to solve for the velocity over there at position A. And so half of the mass times v squared equals that friction force, 9,535.4, times the path length. The path length is the 26 meters. That's how long the skid marks were. Okay, I'm just going to solve for the v here. So I've got 9,535.4 times 26, then I'm dividing by a half, dividing by 1390, and then I'm going to take the square root. So the original speed was 18.887 meters per second. And oh dear, I think we were speeding, because he said the speed limit was 15 meters per second, and we were going 18.8 meters per second.